This is talk scaling reliability, so you want to add a 9. Here, when we're talking about 9s, we're referring to like 9s of reliability. This might be, say, like your success rate, where it's like, I want to make sure that 99% of the requests that I'm receiving, I'm responding correctly. So I'm Moses Nakamura. I work at Twitter. I'm a Finagle maintainer. And you can follow me on Twitter at mnnakamura. So we have a Twitter track today. I hope folks have been attending some of these other talks also. We had a bunch of really good stuff earlier today. And my coworker, Mike Svet, who's right here, is going to be talking about migrating the home timeline from a sort of rigid write-based model to a more flexible read-based model, which makes it easier to interleave relevancy results. So it's going to be pretty interesting, and the home timeline is sort of the most important part of Twitter. So sort of talking about how to migrate that kind of important service is going to be pretty interesting. All right, so basically the core idea of this talk is that reliability is a problem that changes as your organization scales up. And it becomes more and more complicated as your organization gets bigger and bigger. So when people ask, well, why couldn't I just make Twitter in a weekend? Part of the reason why you can't is because of the scale problem. The other part of that is the reliability problem, where you could make a version of Twitter in the weekend, but it wouldn't be able to handle, say, hundreds of thousands of concurrent requests. It also wouldn't be able to serve them successfully. So one question is sort of who cares about reliability? So Twitter cares a lot about reliability. If any of y'all are Twitter old timers, you might recognize this picture. This is the fail whale. Twitter used to be known for the fail whale, which was not a terribly comfortable position for us to be in. Often people would come to twitter.com trying to get their tweets and would instead not be able to get them. That really sucked. This was like 7 years ago. Now if you go to twitter.com, you get lots of tweets. So that's something that we care a lot about. Hopefully y'all care about these metrics also. Some of these things are uptime, like the number of minutes that people can access your stuff per quarter. Dollars, if you make money from your business, then if people can't get to your business, then you might be losing dollars, which isn't great. We care about our success rate. We care about our mean time between failures, like how often do our components fail. And we also care about our mean time to resolution. We care about when our components fail, how long do they fail for. And lots of these things are things that matter a lot to end users. An example of mean time to resolution, if your mean time to resolution is like an hour during the workday, then people are going to really care a lot about that. If your mean time between failures is like every single day, people are going to notice that your site feels like it's never up. It's unreliable. So I mentioned before that I'm a Finagle maintainer. Finagle is a sort of a distributed systems toolkit for extensible RPC. We ended up putting a lot of our resiliency features inside of Finagle, which is an open source library if anyone else is interested in picking up some of my team's work. And it ended up being a pretty good place to put them because every service at Twitter uses them. So as like when we put the feature into Finagle and people redeploy, they're going to get these resiliency features automatically. So sort of when you're sort of starting out, it's like a startup or a smaller company, one of the first important ideas that people come onto is that teams should own their own failures. And this basically makes sense. We're talking about how we want to align incentives for our teams. What we want is we want the people who make the failure have to be responsible for it. So we can't say like, okay, I'm going to go push out a bunch of buggy crap and then like the SREs or the ops people or someone else is going to deal with it. Like you need to own your own failure. When teams have to own their own failures, they begin to start looking at and investigating day-to-day failures, which are things like background like noise failures, like sort of the crap that fills up your logs, like gray failures where there's like maybe network congestion, which makes things slow, or stop the world pauses, which are also making things slow, or Heisenbugs, which are things which are like sometimes bugs, sometimes not, temporarily overloaded hosts, which can't respond to your stuff and just end up giving back failures, and crashes when there's like something that crashes your service and then it just falls over and can't serve any more traffic. Some other examples are bugs. I've actually stopped writing bugs. It made my life a lot easier to not write any bugs more. But most people still write bugs. I don't know why, but as you scale your organization, something you have to worry about is each person who you're adding to your organization is going to also be introducing bugs. This is one of the reasons why we like to add more process as we scale our organizations. Because we care more about each individual bug that people add, we add things like code review, where if we look at the code before we roll it out, then we won't have as many bugs. So one example of a failure that we ran into was, sorry, I'm going to back up a little bit. So sort of the structure of this talk, and I should have started with this, I'm sorry, is that these are a lot of the failures in reliability when these key metrics started going down. And these are ways that we ended up sort of looking at the problem and then trying to solve that problem holistically. These might not be the failures that you get. So if that's the case for you, really what I'd like for people to get out of this talk is sort of an idea of how we looked at the problem and tried to find a simple, clear way to solve it completely. OK, so probabilistic failures is something that we ended up seeing, where it was basically if we sent a request, then it would fail with like, let's say for our imaginary server, 90% of the time. Or sorry, it would be successful 90% of the time. Failing 90% of the time, way worse. So this was not a terribly good success rate. When we're measuring this in terms of nines, we would say this is 1 9, which is not that good. But there's a pretty simple solution to this that probably a lot of people have used before. You just slap a bunch of retries on it. You say, OK, let's keep trying. If you add 2 more retries, then suddenly you can move your service, which was previously 1 9, to 3 9s. So that's pretty nice. What if there's a bug in the release? You go and do your deploy, and suddenly everything goes unhealthy. That's not terribly good. So here we might introduce like a new process thing. We might say canary 1, and when it goes and like dies in a fire, then only one of them is dying instead of all of them. If we have 10 servers and 10 clients here, then what this means is that your clients are seeing a 10% error rate rather than 100%. At some point, as the organization scales, we begin to think, maybe we can do better if we have a team that sort of looks at resiliency. So if each app has 10% chance of failure, sort of going back to our really bad 90% case, then as we scale up, like if we have a microservice architecture, if each tier has a 10% chance of failure, then, sorry, I computed what this would come out to be, but it's in my notes, so I'm going to have to look at my speaker notes. Sorry. So this gives us like an overall 35% chance of failure. If instead we can move it to a 0.1% chance of failure, then it becomes a 0.4% chance of failure. Now, how do I get back to my slides? Present. Thank you. Oh, God. Don't keep your slides in the cloud, folks. Yeah. Anyway, so when we have, so sort of the first slide was the 35% failure when we have the 4 services that are all working in tandem. We had the 10% error rate. On the other hand, the second slide, this one, here if we only have a 0.1% chance of failure, say because we added retries, then suddenly this becomes much less painful. But also these kinds of errors become, or these kinds of resiliency efforts become more important as you scale up. So there are also, we also begin to run into less common failure modes more often when we have more services. One example is if you have more services, one of the joys is that you can deploy more often, but also one of the scary things is you can deploy more often. So people often run into when you do a rolling restart, you try to go and talk to a machine that's either powering down or powering up, and sometimes you're not successful. That's not too good. Another good example is sometimes there'll be a bad remote host. Maybe there's a hardware problem, or maybe it's gotten to a bad state. We can also run into things where mean time to recovery is slow. And this ends up meaning typically either we don't have an automated system in place, or we find it very difficult to have an automated system in place, and we don't have good tools for our operators. So one question that we often ask ourselves, especially when we're thinking about how we can improve our mean time to recovery, is what's happening when our caller is making requests to our receiver? So you can sort of imagine this is a diagram where A is making a request to B, and then B makes a request to C, but it fails. So B retries the request, finally succeeds in making the request to C, responds, and then given that response is able to construct a response for it. So the question we can ask ourselves is, what information would it be useful to have in this chart? So some examples are, it would be useful to know how long did each of these things take? What was the duration first of the request from A to B? What was the duration of the request from B to C? And what about, or for the failure, and what about for the successful one? It'd also be useful to know, oh, we did a retry here. So some examples of useful things that can help us get insight into what's happening inside of servers are exporting metrics, exporting logs, exporting distributed trace data for something like Zipkin or a Dapper-style system, exporting configuration information about your service, and also being able to know which remote peers a client is talking to. Some examples of, I have an Adobe Update Reader thing, which keeps on popping up. I'm sorry about that. Some examples of failures while rolling. You might send a request when the server is trying to spin back up. This can be bad if, for example, the server hasn't finished hydrating its caches, or if it's actually not listening on the port yet, even though you think it is, or if it's just slow because it hasn't JITted its stuff yet. So some examples of things that might happen are maybe you're sending in some requests, and you start getting some healthy responses and some unhealthy responses. One thing that can help us is when we're turning off our servers, instead we send a go away instead of just sort of dying. So basically what happens is the caller sends requests. The server says, okay, wait, take a chill pill. So in HTTP2, we have these nice go away messages, and this is exactly what they're for. And you can encode in them, this is the last stream ID that I'm going to be able to serve successfully. And after that, you're on your own. So go find somebody else who can help you. Another thing that might go on is if you have one bad egg. This is sort of like there's some server that's not behaving correctly. and you are probably at that point not going to want to keep on sending sending requests to that server. Basically, let's say 3/4 of the responses they're sending to you are like, I'm overloaded. I wasn't able to send a response successfully. We don't want to keep on just getting these like bad responses. So if your caller can say, okay, well, this one is sending me like 75% unhealthy requests, unhealthy responses, I should probably stop talking to them. Then you can improve your success rate. As you continue to scale up your organization, we begin to run into even more rare failures. They're sort of like rare Pokemon, but less exciting. So since, as we were saying, each person introduces new failures, if each person introduces a new bug every month, if you've doubled the size of your engineering organization, then you're probably going to double the rate at which you're creating new bugs. So more and more rare failures end up being things like retry storms, where if you were overloaded in a persistent way, then the retries that were previously helping your success rate can now hurt it by overloading your server even more than it was before. These are also sometimes called retry amplification. There can also be environmental pressures, and overloads are caused not by the person who's calling you, but by the person who calls the person who's calling you. So in the retry storm, you can sort of see we're sending way too many requests because we're doing all these retries. This ends up meaning that we can sort of see, as we send requests, you do like a retry, then a request, a retry, then a request. You can see that a pretty big proportion of all of our requests overall ends up being retries. So this gives us a vector to attack. What we've added are these things called retry budgets, where the idea is you can only send some proportion of your overall requests as retries. So suppose that you find that 200% of your requests are retries. That's way too much. You can say, okay, let's dial it back down. How about only 20% of my requests can be retries, after which we just say, you're really unhealthy. I'm going to stop retrying as much. Another thing that can happen is just being regular old overloaded. So this ends up being sort of a queuing theory problem where we're shoving requests in really fast, and we're unable to remove responses off our sort of imaginary queue, which we're modeling the server as fast. And people who know a little bit about queuing theory, you'll know that your queue will basically queue infinitely, which is not really what you want to happen. In this case, what you want is for folks to stop shoving things into your queue as fast. So instead, what we can say is, if we know that we're not going to be able to serve a good response, we can instead very quickly insert a knack. This also has the benefit of telling our client, okay, this might be something we can take an action item on, where we can say, oh, maybe we should do some failure detection and avoid this thing. So the caller is sending requests. Receiver says, now is not really a great time. Caller sends fewer requests. This one is sort of specific to the way that we deploy our stuff. We use Mesos and Aurora. And in order to support co-locating processes, one of the things that we do is we'll throttle a process if it's using too much CPU time. Another thing that can sort of end up happening is for things that we have less good control over, like disk I/O, that can cause weird interactions, which can often end up meaning that you're throttled. So imagine that you're some service and you're sort of chugging along happily, but you get co-located with a very rude service. And this service is just doing all kinds of disk I/O and taking up all kinds of CPU. And out of basically no fault of your own, you're being throttled. You're not in a happy situation right now. But you suspect that maybe the service will stop being rude in another few seconds, and you just need some time to sort of deal with it. So one thing you can do is say, all right, I'm spending like 20% of my time being throttled. That means that I'm probably not going to be able to give you a good response. So I'm just going to immediately start knacking requests so you can know to be routed to another node, which maybe has a better neighbor and isn't being as unhealthy. Yeah, so send a bunch of knacks. After we send all those knacks, then suddenly the receiver has an opportunity to sort of chill out, figure out its CPU stuff. Maybe it was doing a bunch of garbage collections, and recover. So one thing is that this is not just one team that's working on this. So I mentioned there's the Finagle team, but there's also the observability team, where we export all the observability data, but you need to be able to store it somewhere if you want to be able to support the stuff. If you want to be able to decrease your mean time to recovery, one great tool can be automating your stuff. If you see that a single node is like going into a GC spiral, maybe you want to be able to restart it immediately so that it doesn't keep on dragging things down for the rest of the nodes. With our deploys, maybe we want to be able to make our deploys more repeatable and more standardized, and the same across our different teams. When we have a site-wide outage, who is going to coordinate fixing all that stuff up? Also, a lot of these things are generic kinds of failures, since all of these things are things that we put in Finagle and are appropriate across the company. But there are lots of things which are going to have to be specific to teams. And for that kind of thing, we want to be able to have people who can spread these kinds of reliability practices around the organization. One important thing when we have all these different teams is that we want these people to talk about their failures a lot and to do it loudly. It's important that these teams sort of get a global view of what's going on and sort of know, like, okay, well, my success rate is going down, and this is because the client who's talking to me is sending me way more traffic. Or my success rate is down, and it's because the remote host who I'm talking to is having a very bad day. We want to make sure that teams that are trying to improve these kinds of resiliency problems are coordinating so that you're not stepping on each other's feet. When we talk about how we want to be able to solve a problem completely, if you have two teams that are both trying to solve a problem completely, then you might be duplicating your effort. We want to empower our teams, because if we give a team a mandate and then say, well, you can't actually do anything, then you're not going to have good results. You want to make sure that you're keeping a history of your failures. It's a really good reason to fail loudly and with much noise and be proud of your failures, because if you don't, then as soon as the people who failed and were good at failing leave, then you're going to forget everything that you learned from them. It also helps set a good culture in that it helps people know that they shouldn't be hiding their failures or papering over them, and that instead they should talk frankly about them and make sure that you understand how you're going to solve them completely. All right, and that's it. So if people have questions about any of these sort of earlier things where we solved something completely, these are all like the really short versions. So I'm happy to just give you the long version for any one of these individual ones that people are interested in.
Can you go more into the noisy neighbor problem?
Yeah, so the question is for the noisy neighbor problem. Noisy neighbors are, it's like a really complicated problem, basically. So what we do is we have schedulers which are trying to make sure that neighbors aren't allowed to be noisy. So This is one of the reasons why we throttle people who are using too much CPU. And generally, with these schedulers, you have to declare how much resources you're trying to use of a given type. For Aurora, the way that it works, and for Mesos, the way that it works right now, although I think that we're changing this, is that you get a certain amount of CPU time. So you might say, like, I need 4 cores out of this 12-core machine, and what you're actually going to be getting is like 33% of the CPU time. So what this ends up meaning is that you could end up using all of your CPU time like at the beginning of the second, and then for the rest of the second be like, okay. And your scheduler is probably going to help you avoid this kind of problem. But if this is the kind of thing which you're worried about, then it might make sense to end up switching to something which can give you CPU isolation, which is something that Mesos is also looking to give people the option for. Sort of the downside of CPU isolation ends up being that you can't then reap some of the CPU time that other other tasks which are scheduled on the same node aren't using. So there's sort of a trade-off there. And a lot of this stuff does end up being trade-offs. Then there are also certain kinds of resources which we aren't as good at managing right now. Like, for example, disk I/O. With memory, you can use something which says, like, OK, you're using too much memory, and you're just going to shoot you in the head. But sometimes with disk I/O, it can be a little bit trickier. So a lot of it is just like making sure that you're keeping track of how each task is utilizing each resource that must be shared, and making sure that you're keeping people honest. All right. Well, one thing that I think is interesting is retries. So retries are often looked at pretty simply, where basically we're just going to slap a bunch of retries on it. And people say, like, oh, use backoffs or use exponential backoffs. Basically, the reason why we want to use backoffs is because we want to move some of the load temporarily, where right now the problem isn't necessarily that we're overloaded always, but really the problem is that we're overloaded right now. Everyone wants to get their request right now, and because of that, we're having a problem. So by having exponential backoff, we say, OK, well, what if we can instead get the response? Or what if we instead say, not everyone's going to get their response right now, but we can move them to a different time. The problem is there with that if everyone wants the request right now, if we just have a regular exponential backoff, then the time that we move them to will also have too many people who want their requests right now. So then you want to probably add jitter to your backoff, where you just add some random perturbation, which will make it so that you're moving people a little bit more evenly over the time in the future. What's up?
Talk a little bit about retry storms. Have you ever encountered knack storms with the opposite problem? And how do you handle that at a grand caller level, with perhaps many nodes down the chain is doing a lot of knacking, but grand callers can retry much bigger?
OK, so the question is OK, so there can be retry storms. Have you ever encountered knack storms, which would be sort of the opposite, where all of the remote I think what you're saying is where all of the remote hosts are knacking?
Where the large percentage of responses from the target cluster are knacking rather than doing actual work.
Right. So if a large percentage of the hosts in the cluster are knacking instead of doing actual work, then presumably if the remote hosts are acting in good faith, then they're actually all overloaded. So typically what this indicates is that you're sort of sending too much load overall. It could be that you're doing a really good job, your service is really successful, and maybe you launch something new and it's receiving way too much traffic and your backends can't handle it. At this point, typically what the right thing to do is to, or what we've found so far, is to start shedding load. So there can be a few different ways of modeling that your remote hosts are doing too many NACs. One thing is to keep this is something that Google suggested in their SRE book, which we haven't tried out that much so far, but we're sort of looking into right now, is if you keep a histogram of how many retries or how likely you expect a request to be successful, then you can use that in order to decide how to shed load. We're sort of experimenting with this and not 100% sure how it's going to work out. This is part of what we're attempting in order to sort of solve that problem completely, where we know that because you're overloaded, you're actually serving fewer responses than you would be able to if we were sending you less traffic. Where because I'm sending you, say, 200,000 requests per second, and you can handle 100,000 requests per second, you're actually failing down to 50,000 requests per second because you're still being overloaded by so much. So really what we want to do is start instead sending you 100,000 requests per second and just drop the other 100,000 amount of load. All right, any more questions? All right, I guess that's it. Thanks, folks.